Recording in progress. Yeah. Yeah. Comes on everyone. Let's start off. This is the last thing that we did. So we proved, the rotational kinetic energy is half I omega square. And then we said a rolling body is nothing but one translation plus rotation. So you can write this. This is for a rolling body. But then we said, there are cases where system can have multiple degrees of rotations and multiple degrees of translations. So let's see what I mean by that. A question would explain you that better. Let's say we have a rod here. We have a disk. Let's say mass is m1, radius is r. This is a rod. Let the mass be m2, length is l. So the disk is rotating about its own axis with omega 1, and this whole setup is rotating with omega 2. Meaning, if you see now, this setup is rotating like this. Able to visualize how it is? It's like your swinging table fan. If you see your table fan, how does it move? It rotates and plus also it swings. Able to visualize a swinging table fan? So you have a rotation and you have a revolution. Find the kinetic energy of the system. Give this a try. Others, do keep your cams on. Try. 30 seconds more. Let's see. Now this thing can be split into two parts. One, the disk, and the disk and the rod ka rotation. So basically, we have rotation and we have revolution. So you're rotating with omega 1 and you're revolving with omega 2. So for this thing, the energy would be half I omega 1 square. What is the moment of inertia for this? For a disk about the perpendicular axis is m1 r square by 2 omega 1 square. That is the energy for your rotation. What about this guy? Now see here, I want moment of inertia about this central axis, right? So we got a disk here and we got a rod here. So we have two things. Again, half I of the rod plus I of the disk, both are rotating with omega 2 square. Now I of the rod will be m2 L square by 3 because it's about the corner plus, now for a disk, about this axis is mr square by 4. It's a diameter plus parallaxis theorem. So m1 r square by 4 plus m1 L square omega 2 square. Is that making sense, everyone? So you want the moment inertia of the disk about this axis. So what to do? This is mr square by 4 plus ml square. Na parallaxis theorem we have to use. You need to find the total moment of inertia about that axis. There, you got the whole thing. So the kinetic energy of the system will be m1 r square omega square by 4 plus half m2 L square by 3 plus m1 r square by 4 plus m1 L square omega 2 square. There, that's your answer. Check. Is this making sense, everyone? Imagine if there is no omega 1 and this whole system is rotating, you will find moment of inertia about the central axis. So you have to find the rod plus this thing. It is not a point mass god. Is every point on the disk equidistant from the axis?
So isn't it like it's parallel to the
Okay.
axis?
So it is equidistant. Okay. Next one, clear with this? Think about it. That much you should be able to visualize. What is the point of doing tough problems when you can't visualize such a small thing? Seriously, still you can't visualize. God. Alright, God, this would be the distance God for every point.
Oh, okay. Okay, yes, sir. So like from that point, okay, yes.
You have to take the distance from the axis. Is this clear, everyone?
Yes.
You can take directly m into d square for point particles. This is not a particle. It's like asking, so you mean to say, if I said there is a sphere m and r, if I want more differential about this axis, what will you say? ml square. Parallax theorem we have to use. Next one. Everyone got this? Now this is not a mains level question. These are the kind of questions you can expect in advance. They're not tough, but you should know, like, there's most people, right? They try to use this thing there. You need to understand rolling motion has the translation plus rotation. So this is a case where you have rotation plus rotation. Clear with this? That way. So this degrees of freedom concept is quite useful. So when someone asks you to find the energy of a system, before jumping and directly applying a formula, ask yourself, this is what exactly? Does it have a rotation? Does it have a translation? Is it a combination? What? And then based on that, you solve. Let's see some one or two easy ones, and then we'll go ahead. Let's say we got a rod here, mass m, length L, release from rest. When the rod becomes vertical, find omega in the hinge reaction when the rod becomes vertical. This is an easy one. This would be a proper mains level question. Vihan, clear na? Previous one, why it doesn't work? Hmm.
Yes, sir. Like only across that line, that will
ये
be
they'll be
allowing.
equidistant. Side पे
Hmm.
गया तो नहीं होगा.
Yes, sir.
वो just already knows the answer for this. But for Vojas, we can change this. What if the hinge is here, Vojas? L by 4. Yeah, this is a standard model. We have done these kind of questions in work parnijiraum, but pendulum. Similar, instead of a pendulum, we got a rod. Root G by R. नहीं बोल 5 by 2. What 5 by 2 record? Right, Daksha. Okay. Let's see. When the rod has become vertical, so basically the center of mass from here falls and comes here. So that is basically L by 2. Let this be omega. The loss in potential energy is equal to gain in kinetic energy. Now remember, the rod is hinged about the axis, so it is a pure rotation. So this would be mg L by 2. This is equal to half I hinge omega square. There is no translation here. It is only purely rotating about the hinge. So that's how you decide whether should I use half mv cum square plus half I omega square or what. This is a pure rotation. This is mg L by 2 plus half. This would be ml square by 3 omega square. Omega will be root 3g by L. Since it is rotating about the hinge, the energy must be about the hinge. Next thing, you want the hinge reaction. Draw your free body diagram. So this would be Ny, this would be Nx, your own weight mg. Since you are going in a circle, there will be a centrifugal force, which is m omega square r. R must be center of mass ka distance. Therefore, Ny will be mg plus m omega square L by 2, which is 5 mg by 2. Nx is 0. There is no horizontal force. Easy? Any doubts on this? question, right, would have been fun if you're doing like this. Same question if you try to do. I will try, you can try this as a homework. Find hinge reaction when the rod rotates with theta. कर सकते हैं अभी actually. Let's try. I'll give 2-3 minutes. If this rod swings by an angle theta and then find the hinge reaction. At least let's get the equation. Solving, but I will leave it to you. अंश इतना easy नहीं है life. This is a deadly one. This would go to an advanced level question. The previous one was like a small puppy there. The moment I made theta, this became a tiger. Multiple things happened here. First thing, when it has become like this, this is your center of mass. This is your center of mass. This length was L by 2. So this thing has fallen a height of, this is theta. So this thing has fallen a height of L by 2 sine theta. So the first step will be mg L by 2 sine theta is equal to half I hinge omega square. So yeah, so omega you will get. Then when you draw the free body diagram, now say I would suggest you do it this way. Take ny this way and nx this way. You can take ny nx any direction. Reason, this guy, it is going in a circle. It has two accelerations. It has a centripetal. It also has a tangential. isn't it? This also has a tangential acceleration. Now, if this angle is theta, and if you take this to be mg, this angle would be, how much is this? This would be 90 minus theta. That means if you take the components here, this guy would be mg sine theta. This guy would be mg cos theta. Most people ignore that A tangential. When I ask you hinge reaction, it is root over nx square plus ny square. Previously, that nx became 0. Now it won't be 0. So why can't I take up and down? You can do that. But up and down में problem क्या है ना? You have to resolve acceleration into components. I don't want to do that. I don't want to resolve A centripetal and A tangential. But you can do that. Nothing wrong with this. Because if I do this thing, I just have to resolve only mg into components. Now write the forces along the thing. So this will be ny minus mg sine theta is equal to mass into centripetal acceleration, which is m omega square L by 2. From here, you'll get ny. What is nx? Nx would be, we need to find A tangential. Nx plus mg cos theta is equal to mass into A tangential. But how do you find A tangential? A tangential is R into L by 2 into alpha. But how do you get alpha? This is your equation 2, is equation 3. You have to take torque about the hinge. If you take torque about the hinge, then we have only mg cos theta ka torque. So mg cos theta into L by 2 is equal to I about hinge into alpha. From here you get alpha. This is your equation 4. That would be ml square by 3. So this will get 3g cos theta by 12. You take this and substitute here. So it is not really that tough, but it is lengthy. You have to use energy, then we have to use torque equation, then we have to use two force equations. And then you can do nx square plus ny square. That would be the final answer. I'll leave the steps to you. How do you find A tangential, right? You won't get it directly. A tangential is R alpha. And how do you get alpha? You get alpha from taking torque about the hinge. So in order to find ny, I need omega, that comes from energy. In order to find nx, I need alpha, that comes from torque equation. So we have two NLM equations, one torque equation, one energy conservation. Is this clear, everyone? Previous problem was easy because nx ka problem nahi tha. That alpha was 0. Is this clear, everyone? It's a good one. Not really that tough, but it's a good one. Compared to the previous one, you can see the complexity of the problem. The moment I made theta, the complexity increased. Clear now, everyone? Ansh, got this? Devansh? Sharman? Next one. We have a bowl kind of shape here. This side is rough and there is no slipping. This side is smooth. So the border above it becomes smooth. So we have a solid sphere. Mass and radius are released from height h. Let's this point be A is the lowest point. Find V and omega when it reaches A. Find the ratio of kinetic energy of translation by kinetic energy of rotation. Find the maximum height it goes on the other side. So after rolling and enters the smooth surface, how much height it will go on the other side? So initially the ball will roll and come. Once it crosses A, it becomes smooth surface. So find the speed at A, V and omega, find the ratio of kinetic energy and translation energy. And what is the maximum height you will go on the smooth surface? Anyone didn't get the diagram, please ask. Root 2 GH, seriously? When you leave the body without any rolling, you will get root 2 GH. Now it is rolling also. Okay, that is right, Puroja. Get the next one. I'm more interested on the third one. Maximum height on the smooth side. If I ask you, that would be the actual question. Let's see the speed part. So when the ball comes here, this will have speed v, this will have omega. This is state 1, this is state 2. Energy in state 1 is equal to energy in state 2. It's all conservation of things. The only difference is in kinetic energy, instead of half mv square, now you'll write half mv square plus half I omega square. This will be mgh is equal to half mv square plus half ICM omega square. It's a rolling body. Don't forget that. For a rolling body, the formula is kinetic energy of center of mass plus kinetic energy about center of mass. So this would be mgh, and it's a solid sphere. So that will be 2 by 5 mr square. And we know r omega is equal to v here. So basically v minus r omega will be v ground. That is the actual equation. And v ground is 0. Therefore, v becomes equal to r omega. Be careful. Never say v is equal to r omega is no slipping condition. The point of contact should have same velocity. That is a no slipping condition. So 2 will cancel. This would be mgh is equal to 7 by 10 mv square. There. So v is equal to root 10 gh by 7. The kinetic energy of translation by kinetic energy of rotation will be half mv square by half I omega square. I is 2 by 5 mr square omega square. Half of will cancel, we'll get 5:2 ratio. So the energy will split in that ratio. R omega is V, so you can cancel out. Question still not over. Now this thing will start climbing to this side. You will reach state 3 here. This is height h. How do you find h dash? Try. I'll give you another minute. नहीं बोल रहा था. What makes you think I'm such a good person? I'll make your life easy. Vihan got it. We have one answer. We just don't know the answer for this. We just did get it. Arush got it. See, the catch in this is once you enter the smooth surface, ask yourself, what are the forces acting on the system? We have the normal reaction, we have the mg. There is no friction because it is smooth. So if you look at the torque about the center of mass is zero. Therefore, alpha is zero. Therefore, omega is constant. There is no force to stop your omega from rotating, isn't it? Think about it. If I take a ball, if I spin it and put it on a smooth surface, what will happen? It will just spin there, right? Isn't it? If you take a smooth ball and just keep it there with an omega, the ball will just keep spinning there forever. It will not go front, it will not come back because there is no friction. Is that making sense? So that means when this thing omega is constant, therefore omega doesn't change. So when the ball reaches the topmost point, this will have, omega will still remain there, same omega, but velocity becomes zero. Is that making sense? Whereas on the left hand side, if you observe here, there is a torque due to friction. So the friction is actually generating the omega here. So here, torque about center of mass will be Fr. So this actually gives you I alpha, but there is no torque on the right hand side. So therefore, energy in state 2, energy still comes out though. This would be half mv square plus half I omega square. This will be mg h dash plus half I omega square. So basically only the translational kinetic energy becomes the height. The rotational kinetic energy will remain same. Is that clear, everyone? So if you take a rolling ball and put it on a smooth surface, the omega doesn't get affected because there is no one to generate the torque to change your omega. That was a catch in the question. Next one. Next one. We have height h. There is no slipping. We have a hollow shell, mass m, radius r. It is filled with non-viscous water. Non-viscous meaning there is no friction. Mass is small m. So case 1, we have water inside. Case 2, the water is frozen to ice. So you made that into an ice ball. Water is frozen to ice, which gets stuck to the shell. You get in the two cases. Case 1, we have water. Case 2, someone froze that water inside. It became a solid ice ball. Find V when it reaches the ground. There's no slipping. This is another good one. Conceptual, advanced space question. Not tough, but you have to think a bit. Hope the question was clear. You went your route to GH. I'll punch you now. Shell won't rotate, yeah. Don't say route to GH, right? Gods. Route to GH, when will you get? If you take a particle and if you leave from a height h, you will get V route to GH. No rotation, nothing, you will get route to GH. You have rotation, moment of inertia. What is rotation doing then? Poor thing, it will just die. Solve. The first case, omega, the wall and water. I don't know, just. You got a minute to solve for the first one. Get them both. Actually, first I get the second way आ back to back. I'll give you 2 minutes. Whatever it is, figure it out. The moment I tell you the first one answer, second one you'll figure it out. So both are related actually. If it was a simple mains level question, I would ask you who will reach the ground with more speed. That would be a simpler question. But I'm asking you find the speed. That will be more fun. इतना अच्छा आंसर नहीं आएगा रे gods. There is a capital M and small m. How the hell are you guys cancelling m का values? Mass of the shell is capital M. Mass of the water is small m. Maybe I wrote it in green, so you can't see क्या? Wait, I'll change the color. Actually, we had one guy in the other class who can't see green color. There. Small m. Masses are not equal. Just write the equation. Don't worry about simplifying. Did anyone find out what's the difference? See, I'm telling you, you can't get root 2GH. Someone tells me answer is root 3GH. Hmm. Root 6m plus mgh by 5m plus 3m. Yeah, that looks complex enough. Let's see what is the catch. So case A, when it is water. Case B, this becomes ice. Okay. Now see, the difference is, suppose if you take 3 points here, okay, A, B, C, and if you take a point D on the shell, Now, because there is no friction inside, the water will never rotate. Think about it. If you take a bucket of water, right, and if there is no friction, if you put your hand inside and try to rotate, what will happen? Your hand will just slip, right? That is the reason if you try to catch the sand in the beach, right, it slips through your fingers because it is very smooth. It just passes through the gaps. You cannot rotate a water which does not have friction. Is that making sense, everyone? Getting it? So in this case, when it is non-viscous water, water does not rotate. That means when this ball comes down, you know how it will look like? So when the ball comes down here, this liquid will remain exactly the same way, meaning these points A, B, C will be the same way. They're just, translating. Whereas the point D will be somewhere here. The point D has rotated. Makes sense. So the water does not have any rotation. So here, when you write the energy, loss in potential energy is gain in kinetic energy. Whereas in this ice ball, no, the diagram would look like this. If you take these 3 points here, A, B, C, they'll become like this. They will actually rotate. The ice ball rotates. So basically, the ice ball behaves like a solid sphere. And remember one more thing, you cannot treat the whole thing as a solid sphere because the density of the ice and the density of the shell is different. You cannot treat them as one big solid sphere. It is a non-uniform solid sphere, isn't it? You have to treat the shell and you have to treat the ice ball separately. You can't say the total mass is m plus m and then use 2 by 5 m plus m r square. So what is the loss in potential energy? M plus m. Even the water will have potential energy. Kinetic energy will be half mv square plus half I omega square, which is 2 by 3 mr square omega square. This is for the shell plus half small m v square. This is for the water. And if you observe, there's no rotational component. Simplify that, you'll get the answer. Now, in this case, loss in potential energy is m plus mgh. Everything will look same, half mv square plus half 2 by 3 capital M r square omega square. This is for the shell plus half small m v square plus half 2 by 5 small m r square omega square. This is for the ice ball. The ice ball behaves like a solid sphere. You have to treat them separately. You can't treat them as one solid sphere of mass m plus m because it will be non-uniform density. So can you tell me then who will come faster? Water or the ice ball? Water, no? Because some of the energy is used to rotate the ice ball. Are the steps clear, everyone? This is the thing, if you remember, I explained you in Centro Musca beginning May, what is translation, what is rotation, do you remember? So that is the meaning of this. The water is in a pure translation here. The water will simply slide in a straight line. It doesn't rotate. Whereas here, the ice ball will actually rotate. Clear, everyone? There. It's not a tough one, but conceptual one. You should know, okay, it doesn't rotate in this case. Anyone has not clear with this thing, please ask. Next one. Turn in the page. We have an incline. We have seen this in momentum. This is a better one. This is smooth. This is 2m. Here there is no slipping. Here we have a ball of mass m. Radius is smaller. This track car radius is capital R. Be careful, there are two different radius. The track car radius is capital R, ball car radius is small r. Same question what I asked you there. Find the speed of the ball and the normal reaction when it reaches A. You're not able to visualize non-viscous water, meaning it's a frictionless surface, right? Just like for solids we say frictionless surface, for liquids we say it is non-viscous. Meaning if you won't be able to catch, if you try to put your finger in a non-viscous liquid and if you try to spin, the liquid won't touch your finger, it won't get attracted to you. If you put your hand in the water, your hand gets wet. If you put your hand in a non-viscous water, it won't even touch to you. It's hydrophobic. Did you ever try to touch mercury? Kind of. It's not exact thing, kind of. Meaning you won't be able to move it with your finger. If you put your finger and try to move, your finger will just slip through inside. Kind of like that. I think the best example would be, think of like this. Dry as ka smoke dekha kabhi? Air is there. Air is a non-viscous kind of thing. Kind of. You can put your hand through the air and it just slips through your fingers. It's a hypothetical thing. They don't exist, but same thing like a frictionless surface doesn't exist.
Okay.
Take it a solid cylinder लेते हैं. हर बार sphere we are taking तो we are being racist. So we will give cylinders also a chance. There. They don't mention anything is always in the ground frame. Root GR. I hope you have not taken V is equal to R omega. If you have taken no slipping condition as V is equal to R omega, you are gone. That keep that in mind. 10 times I keep telling you, no slipping condition is not V is equal to R omega. When you're on the ground, it does happen, not every time. Let's say, and you know the process, exact same question we did there, and this thing, momentum. So when the ball reaches here, let the speed be V1, let this rotate with omega, let this go with V2. There are no horizontal forces, conservation of linear momentum. P initial is equal to P final, 0 is equal to mv1 minus 2mv2. This is the same equation. V1 is equal to 2V2. Conservation of energy. mgr is equal to half mv1 square plus half 2m. There is also rolling motion now. Half I omega square. This is for the ball, plus wedge will be half 2m v2 square. This is equation 2. Where will I get equation 3 from? Ojas, where did you get h from? And you got speed root 8gh. Why? After telling you all n times, you can't get more than root 2gr. Why the hell are you guys getting answers more than that? Meaning it's a good thing, if you can actually do this, you can solve the world energy crisis. So I do understand. On your planet, maybe it does happen, a perpetual motion engine where you can get free energy out of nowhere. So please do make sure your engine works properly. You can actually save the world from energy crisis. You are the future. Whoever gets answer to greater than root 2gr, remember, you are the pioneers of the future energy research. You should not be here. You should have got a Nobel Prize by now. Unfortunately, we humans are not able to understand your research, so we are too primitive. So remember the taunt next time when you get an answer greater than root 2gr. What is the no slipping condition? Now, if you look at this, at this point here, I'll just draw this. So this guy is going with V1, this is going with omega. So this point has a velocity r omega, and this is going with V1. And the floor which is there, the wedge here, is going back with V2. So the no slipping condition says the velocity at the point of contact must be same. This is your no slipping condition, everyone. You can't write V is equal to r omega. This is the no slipping condition. And I know V1 is equal to 2V2. I can simplify this. So I get V2 is equal to r omega by 3. And V1 is equal to 2r omega by 3. There, I know everything. Dump this in equation 2. Take this and put it in equation 2. So we get mgr is equal to half m v1 square. That would be, I can do one thing. I'll just change omega only there. mgr is half mv1 square plus solid cylinder is mr square by 2 omega square plus m v2 square. V2 is how much? V1 by 2. So this is mgr. R omega is 3v1 by 2. This is m by 4 and r omega is 3v1 by 2 ka square plus mv1 square by 4. Yeah, numbers are not that great, but how much is this? This is half plus 1 by 4 plus 9 by 16. This is 3 by 4 by 9 by 16. Multiply 4 and 4. That would be 12 plus 9. Okay, that is 21 by 16. 21 by 16. So V1 will be root over 16 GR by 21. I hope I'm right. Right, Ansh got the same thing. Check it out. एक बार V1 आ गया, V2 आ जाएगा. Everything will come in one after another. Clear? There is still one more part. You have to find the normal reaction. Check the steps. So if you got the 3 equations, your job's done. Most people goof up the no slipping condition. Just be careful with that. You can't write V1 is equal to R omega. Now, actually, the relation is V1 is 2R omega by 3. And how do you find the normal reaction? You know the catch. There are 2 things you have to be careful here. N, mg. The thing is going in a circle with respect to this guy, who himself is going with V2. This guy is going with V1. So we have a centripetal acceleration is V relative square by radius, which is R minus R. you have to subtract the radius of the sphere, which will be v1 plus v2 whole square by r. So there, so normal reaction will be mg plus m v1 plus v2 square by r minus r. I will leave it. You can substitute and get the answer. Do you guys remember that, na? V relative square by r. That is a catch. But here r ka place mein r minus r aayega. We have to take the center of mass ka distance from the center. Have a look at this. Look at the three equations. Ask me if you're confused. Got this? Let's see the next one. Clear, na, Surya? Niharika? Daksha? Clear? Arush? Ahana? Adi? Clear. Next one. Next one would be another advanced paragraph question. Again, you have seen this in work per energy. We have a solid sphere, mass m, radius r. We got a circular track here, capital R. So from the bottom of this till here, this height is h. This is the horizontal position here. There are two questions here. First question, find h minimum if ball reaches the topmost point of the circle. Basically the vertical circular motion. There is no slipping anywhere. That is fine. Second question, if h is equal to h minimum, find acceleration of point B when the sphere comes to the horizontal position. B is a point on the circumference. Huh? You getting what I'm asking? I'm asking when the sphere is rolling, there is a point on the circumference. So that is this point here. So when the sphere comes to this position, I want the acceleration of this point. B is a point on the circumference. There. Let's get the first part. I'll give 2 minutes for part A. Find the h minimum to complete the vertical circle. Let's get that. The second part we will see. 7r by 5. Yeah, that is wrong. You didn't even include small r everywhere in the picture. And it is definitely wrong. You know why? How can I tell so confident? Think about this. What is this height? 2r. Agreed? Where will the 7r be 5 be? It will be here. You're also a pioneer in energy conservation. You can go from low height to high height. Now, this kind of thinking is important in a way. That is how you can actually eliminate options in the exam. So normally when I solve a question, right, I see like, okay, in this question, the answer should be somewhat like this. Meaning one thing I'm pretty sure, answer must be greater than 2r. I can even tell you something better. The answer must be greater than 2.5r. Do you guys remember in that no slipping thing, when it is smooth surface, the height is 5r by 2. If you remember in vertical circular motion. Now here the ball is rolling also. That means you definitely need more than 2.5r. You can't have an answer less than 5r by 2. 20r by 7. Let's see. And the final answer does include small r. Most of you are not getting it. What is the catch in this question? The question and the catch is at the topmost point, you can't have a zero speed. Agreed? Just think about it. If you have zero speed here, what will happen? You will fall down now. To complete the vertical circular motion at the highest point, the centrifugal force must balance the mg. That is how we did the entire vertical circular motion. So when this sphere reaches the topmost point, if you look at the forces, we have mg, we have normal reaction, we have centrifugal force mv square by r minus r. So from here we get normal reaction will be mv square by r minus mg. This must be greater than equal to 0 because you are reaching the topmost point. So v square will be r minus r into g. So this is the minimum speed at the highest point. If you don't have at least this much speed when you reach the top, you won't even reach the top. This is the first thing. Right? Then conservation of energy. This is state 1. This is state 2. I will take the ground as a reference line. Energy in state 1 is equal to energy in state 2. Initially, we have only potential energy, mg. Remember, potential energy is always from the center of mass. mg h plus r. Finally, what is the potential energy? mg 2r minus small r. Did you realize that? Because you have to take the center of mass at this height, na, you should take. It is 2 capital R minus small r. The center of mass is, you should take always the center of mass height from the reference line. Plus energy will be half mv square plus half I omega square. Simplify this. This guy would be mg h. Send that r this side. You will get mg 2 capital R minus 2 small r. This is a half mv square. I will be 2 by 5 m small r omega square. Here it is not slipping, so v is equal to small r omega here. This would be mgh, mg2r minus, I'll just take out 2 common. This would be 1 by 2 plus 1 by 5, 7 by 10 mv square. Now bring that v square and substitute here. There, you end up with h is equal to m will cancel 27 by 10 r minus r. That is your minimum height. Have a look at this. Next one. Question still not over. The main question is the B part. If h is h minimum, find the acceleration of that point B on the circumference. This is a good one. Right? Think. I'll give you a minute or two. If you even get the steps, what the hell is happening, that's pretty good.
So could you show the solution for the A part?
That has nothing to do with the B part actually.
Okay, sir.
Did anyone figure out what's happening? See, there are two things happening here. Now, you can't actually see. Suppose if I ask you like this, can you tell me what is the path of B? How is the path of B? It's like a jalebi, right? A spiral jalebi. Complex to study. But if I ask you what is the path of the center, that would be this curve, na? The center is going in a circle, and this point B is going in another circle, isn't it? The path of B is actually circle plus circle. It's going in double circular motion. Think of like this moon with respect to sun. Earth is going around the sun, and moon is going around the earth. It's a rotation plus rotation there. So this is what happens. So first we need to calculate few things. When the sphere is here, this will have a speed v, right? And this will also have an omega, but this will also have an acceleration of center of mass, and this will also have an alpha in the opposite direction. Now, if you look at the forces acting on this, we have mg, we have friction. So if you take torque about that point A, we will get mg into r is equal to ia into alpha. It's a solid sphere, so alpha will be 5g by 7r. And A center of mass will be 5g by 7. So the speed is actually decelerating. Speed is decreasing, right? So at that instant, the center of the sphere is going down with 5g by 7 acceleration, but velocity is still up. Alpha is also backward, which is 5g by 7r. And at this point, how to conserve energy? So the ball is released from here. This is state 1 and this is state 2. So we can conserve energy from state 1 to state 2. Initially, the potential energy is mgh plus r. Now the potential energy is mgr plus half mv square plus half I omega square. I is 2 by 5 mr square omega square. We can solve this. I can get v from here and omega from here. I will leave the working to you. Great. Now see what is happening. So if I ask you what is the acceleration of the center, this part is clear. This itself is a question. What is the acceleration of the sphere when it is at the horizontal position? It's not g, it is 5g by 7 downward. That is the reason speed v is decreasing. No? It doesn't have a constant speed. Right? Next thing. Now from here, see. So this is point B now. Now, if you ask the circle, what is point B doing? What do you think it will say? If you go and stand on the center, and if you look at B, this thing will have two accelerations. It will have a centripetal acceleration AC, which is omega square smaller. It will have a tangential acceleration AT, which is equal to R alpha. So acceleration of B with respect to the center. So the center of the sphere will think B is having tangential and centripetal minus R alpha. This is small r alpha minus small alpha I cap minus omega square R J cap. Great. But your center itself is going in another circle, isn't it? You get in the problem here? The observer at the center of the sphere will think B is going in a circle, non-uniform circular motion, but your center itself is going in another circle. So acceleration of the center with respect to the ground will have again two accelerations. So this will have a centripetal, which is V square by R minus R, and this will be a tangential, which is 5G by 7, which we just calculated. So this would be minus V square by R minus R I cap minus 5G by 7 J cap. There. So acceleration of B with respect to ground, you cannot do directly. So B actually has four components of acceleration. Acceleration of B with respect to the center plus acceleration of the center with respect to the ground. Does that make sense? If you go in a circle, you'll have a centripetal, a tangential. Agreed with that statement, right? So my center is going in a circle. So shouldn't it have a centripetal and a tangential, two components? Now, when you go and stand on the center, B is also going in a circle. Making sense? The center of the sphere thinks B is going in a circle. So you'll have a tangential, a centripetal. But the center of the sphere itself is going in another circle. So the center will have a tangential and a centripetal. So B ka acceleration will be B ka acceleration with respect to the sphere ka acceleration with respect to the center. It's like this. I want to study moon from the sun. I can't do it directly. I'll study moon from the earth, then I'll study earth from the moon, sun. Is the steps clear, everyone? You just add them up, you'll get the final answer. Question is lengthy, complex. This is a kind of a question which is tough also, which is lengthy also. But more than that, you can see there are multiple ideas there that you can learn. Don't think like exact same question aa jayega. Is this clear, everyone? Clear with the steps? Take a break. Come back by 7:05. Any doubts so far? Okay, come back in 10 minutes. Yeah. We have a carpet here. There's no space there. I didn't draw it properly. It's a tightly wound carpet. You can treat this like a solid cylinder. Mass M and radius R. Now someone gently pushed it, and then you know what happens. So this carpet rolls down like that. It becomes radius R by 2. So this carpet starts rolling on the floor. Without slipping. Able to visualize how it is? Kind of like this. So we got a carpet roll here and you just pushed it. Movies mein they show na, hero comes with an entry and the red carpet he kicks it, rolls and goes, like something of that sort. Finds the speed of the carpet. So this carpet doesn't just have a thing, it will actually moves with some speed v. And don't forget it's also rolling also. So find the speed of the carpet when the radius becomes R by 2. Let's get this. GR by 3. Okay. Let's see. So what is the catch here? So this is state 1. The center of mass is here. So potential energy is mgr. Kinetic energy is 0. Now when the radius becomes r by 2, what happens to the mass? Does the mass remain same? This becomes mass m by 4 and r by 2 na. And where is the center of mass now? The center of mass is at a height of r by 2. So now the potential energy becomes m by 4 g r by 2. And what about kinetic energy? Half mv square, but remember m has become m by 4 v square plus half I omega square. That's it. Conservation of energy basically. All the potential energy that is lost, that is becoming the kinetic energy. So mgr is equal to mgr by 8 plus 1 by 8 mv square. What is moment of inertia? It's a solid cylinder. So mr square by 2, but m itself become m by 4. R by 2 ka square by 2. That is your I omega square. Is that making sense? mr square by 2. M is m by 4 and r is r by 2 for the small cylinder. And the best part is this. What is the no slipping condition? V is equal to r by 2 omega. The radius has become r by 2. Don't write V is equal to r omega here. V is equal to r by 2 omega. This is the no slipping condition. So there are multiple places you can goof up the mass ka part, the radius ka part, the velocity ka thing. So it's more of a that headache ka thing. The problem is that there are many things changing. You're done. Then basically you just have to substitute mgr. This is shifted this side. This will be 7 mgr by 8. And this is 1 by 8 mv square plus, how much is this? 4, 4, 16, 64 m by 64. What is r omega? 2v square. That will be 4, so you'll get 16 there. 1 by 8 plus 1 by 16. 3 by 16 mv square. So v will be, m goes off, root over, it 2's are 14 gr by 3. I don't know. Check the calculation. Got the working area? There. So basically, a cylinder of m and r becomes a cylinder of m by 4 and r by 2. That's the whole catch. What is the potential energy of a system? Aryaman. If you take a body and if I give you like this, what is the potential energy of a system? If I give you a rod and if I ask you find the potential energy, how do you calculate?
mg into center of mass.
So for a solid cylinder, where is the center of mass?
Center of mass. Got it.
Clear, everyone? Question was easy, but you have to be careful. There's a lot of places where you can mess up one term. And I'm pretty sure like someone must have, you took V is equal to R omega. I was about to take V is equal to R omega and then suddenly it clicked, no, wait, the radius has changed. Maybe mass you must have messed up. So check it out where you goofed up. Clear with this? Next one. So these are, these are advanced level questions only. They're not tough to solve, but there's a high chance of messing up something. Advanced, these are like moderate level. This is a solid sphere. Mass m and radius r is going with V, omega. There is no slipping. I want you to find the kinetic energy of the upper hemisphere. I don't want total. Find kinetic energy of the upper hemisphere. What do you guys think? Upper and lower hemisphere, which one will have more energy or both are equal? If I ask you the upper hemisphere and lower hemisphere, who has more energy? The upper one. Why? Because if you look at the velocity on the upper part, it is v plus r omega. Niche, it will be v minus r omega. The points in the upper hemisphere are going faster than v. The points in the lower hemisphere are going slower than v. So upper hemisphere definitely has more energy than lower hemisphere. Get this? Find the kinetic energy of the upper hemisphere. PE. What PE?
The upper
What is
hemisphere
P?
has like potential energy as well, higher potential energy.
So, but I have talked about kinetic energy here. Please find what is being asked. Don't create your own questions. I did. I said total energy of the upper hemisphere. We are talking about kinetic energy. कभी हुआ? You go to the restaurant and you ask, give me idli. Sir, हमारे पास डोसा अच्छा होता है. नहीं, I just want idli. नहीं, sir, you should try, sir. Uttappam and dosa is super. नहीं यार, मुझे इडली चाहिए. Sir, uttappam and coffee should try. Like, what do you feel like? अरे यार, boss, give me bloody what I'm asking, na? Why you want to sell what you have? Same thing. Teacher is asking kinetic energy. Don't find potential energy. Get this. That happened to you. Happened to me. And then he says like, sir, idli nahi hai. Sir, you should say that, right? Why are you just bloody trying to sell something? I had to order uttapam only. Let's get this. Take a minute. See. So the kinetic energy of the upper hemisphere. Now, if you remember the formula, now this thing is actually having a translation plus this thing. Kinetic energy of center of mass plus kinetic energy about center of mass. So for rolling thing, this thing is still valid. Where is the center of mass for hemisphere? For hemisphere, center of mass is somewhere here. 3r by 8. Someone did calculate, you got a good answer. Let's see, maybe you're right, or I don't know. I never calculated this thing completely. Speed is v plus 3r omega by 8. Are you getting this? So for the upper hemisphere, center of mass ka velocity is 3r omega by 8 plus v. So if you don't know your center of mass ka formulas, you will be gone. So this would be half. Again, you have to be careful now. Mass has become m by 2. You are taking only half of the hemisphere. M by 2 v plus 3r omega by 8 whole square plus half I center of mass omega square. Now, what is I center of mass? That itself is another calculation. This is the center of mass. This is your center. You know about the center. You want about the center of mass. This is 3r by 8. So IO will be I center of mass plus parallax's theorem, which is m by 2. Remember, mass has become m by 2. That's a mistake. Generally, people do. They get everything right, they mess up the mass. 3r by 8 whole square. But what is I naught? I naught is 2 by 5 mr square for a solid sphere. But again, mass has become half. 2 by 5 m by 2 r square. There. If you solve this, you'll get I center of mass from here. Now take that and substitute here. Then you'll get the kinetic energy. It's lengthy. Ansh did the same. Got the steps. If I ask you kinetic energy of lower hemisphere, what will change? Speed will be v minus 3r omega by 8. But the rotational part will remain same. You're getting it? Only the transition will change, rotation part will remain same. Have a look at the steps. To find the center of mass for the upper hemisphere, find the velocity, and then rotation there. Clear with this? It's a good one. If you see, it looks easy to calculate, right? But once you have to find ICOM, again, it goes mad. It does become lengthy. The idea is that if you want only for a part of the thing, you do this thing. Next one. We have a solid cylinder. We have done this last time. There is no slipping. This is H. Find mu minimum for no slipping. If mu is mu minimum by 2, find V omega work done by frictional force, work done by torque due to friction. So even torque does work, force does work. Both are different actually when it reaches the ground. Literally all these things we did last 4 or 5 questions are proper advanced ones. Get them. The first part we have done last class. So get the first part, at least that much so you can handle it. If you have revised the notes last time, you will know. I think last time we did solid sphere, na? This question, somewhere we did that. Okay, let's get this. I thought we did this. Get the mu minimum. R tan theta by 2. How that did you get R, regard? Mu is a dimensionless quantity. I gave you the height, na? Forgot to give theta. Theta is there. Huh? So what are the forces? Friction. Remember, don't take maximum. It is not slipping initially. Mg sine theta, acceleration, and alpha. Take the torque about the bottommost point. So torque about A will be mg sine theta into R is equal to IA. It's a solid cylinder, so mr square by 2 plus mr square, parallaxis theorem, 3 mr square by 2 alpha. Alpha will be 2g sine theta by 3r. Acceleration is r alpha, which is 2g sine theta by 3. Then you want to find friction, so it is mg sine theta minus friction is equal to ma. Then we get friction is equal to mg by 3 sine theta. But we know friction must be less than equal to mu mg cos theta. Therefore, mu must be greater than equal to tan theta by 3. So this is your mu minimum. Now you're saying you're giving half of this. So that means the body won't, it will start slipping, isn't it? If you give less than this, the body will slip. Right? Then comes the second question. Find V and omega when it reaches the ground. Find work done by frictional force. Find work done by frictional torque. Have a look at this page. Any doubts on this thing? This is how you find friction and mu. Let's see. Mg sine theta. How did you even get that? Did you just do F into displacement? You can't do that. Is the point actually moving? If you look at the thing here, now it is slipping, isn't it? This point is skidding. We can't find the displacement directly of that point. So now if you give mu is equal to mu minimum by 2, now the body slips. So listen carefully, it's a good one. it's actually easy only, but you should know the concept. Because most people know up to the rolling part, but once it slips, people become a little clueless what is happening. This will be F max, which is mu mg cos theta. This we have done. So acceleration actually becomes constant. Now we can't take torque over the bottommost point. A is non-inertial because it slips. So mg sine theta minus mu mg cos theta is equal to ma. From here we'll get the acceleration. Now I can substitute the values of everything. And if you take torque about center of mass, you can always take torque about center of mass. That's a savior. Now friction ka torque will come. F max into R is equal to I center of mass into alpha. From here you'll get alpha. Now this height is h. So if you use s is equal to ut plus half at square, this will be h by sine theta. Initial velocity is 0. Acceleration you know. From here you'll get the time taken to reach the ground. Once you got this, we can use v is equal to u plus at. U is 0, so we get 80 here. Omega final is equal to omega initial plus alpha t. From here you can get omega final. There, this is the final speed and the final omega when it reaches the ground. And be careful here. V final, V is not equal to R omega final. It is slipping. Have a look at this page. Clear? Now the next part. Now, if you see, when you say work done by external forces is what? Change in potential energy plus change in kinetic energy. Now here in this body, what is the external force? Friction, right? Think about it. mg goes in potential energy. So change in potential energy is how much? Final minus initial, final is 0. Initial potential energy is mgh. Kinetic energy, initial final kinetic energy is half mv square plus half I omega final square. Initial kinetic energy is 0. This is the work done by frictional force, which is actually negative. Basically, the system is losing energy. But what is work done by frictional torque? What is this formula? When you write work done by all forces, we get change in total kinetic energy. So basically, this thing consists of rotation plus translation. Tell me one thing, if you apply torque, can the body ever translate? Torque is only used for rotation, right? Therefore, work done by torques is change in rotational kinetic energy. There. So forces can change. See, because forces can create torque, they can change omega. Forces can change velocity, but torques can change only velocity. So work done by frictional torque is half I omega square, which is actually positive. So what is actually happening with the story? See, the frictional force is doing two things. Look at this thing. When the friction is acting backward, it is stealing energy from the translation and it is giving energy to the rotation. You're getting it? The torque is doing a positive work, but the net work done by friction is actually 0 because you're stealing more and you're giving less. When there is no slipping, you know what is happening? Whatever energy you're taking from translation, everything you're giving for rotation. So in that case, there is no energy loss. But when it is slipping, some of the energy that you're taking from translation, you're not converting into rotation. It is becoming heat or something. So total work done by friction is negative, but work done by torque due to friction is positive. Now, this is a concept which you should have an idea about it. That work done by torque is only change in rotational kinetic energy, whereas work done by force is all types of kinetic energy. This is clear, everyone. This is a little different. Have a look at this page. Again, a pretty good one. This one and this one, right? 55 and this one are pretty deadly ones, 58. They're good ones. These are the kind of questions, which will actually level up your subject. These tough questions, you might think like, oh, sir, itna idea kahan se aayega? But now you learned it. So more problem is that people think, oh, it's not a tough question. The thing is actually the other way around. It's an opportunity. When you are exposed to tough questions, when you get used to them, then the normal questions also start feeling like manageable. Anyways, it is all in the mindset. You can think it's a problem or you can think it's an opportunity. Clear with this? This I have clearly seen in your seniors also. If you see a kid who scored 5 out of 100, right? And how do you react matters a lot. One kid will start crying, feeling bad, and like, sir, pura gaya, what is this score? I'm gone, I'm good for nothing. That is one way to react. Another guy, oh, I got 5 out of 100, matlab I don't know anything about this chapter, means I need to learn a lot. Good thing it happened today. Imagine if this happened in the final exam. You're getting it? Same marks, but the way you think is different. The second person thinks, imagine it, good thing it happened today. Imagine if it happened in the final exam. Itna you recently only one of your senior he got typhoid right now. He's in hospital from last 1 week. His parents are feeling bad, like, sir, he's losing his time for preparation. You know what the kid says? Acha hua na mummy, abhi aa gaya. Imagine if this had come in Jan 2nd or 3rd week. I couldn't even go to the exam then. I said, like, yeah. Meaning that is how you think. Next one. So we can actually formalize this. So we have work and power due to torque. So we know work dW is integral f bar dot ds. So if a particle is going in some curve, if this is some radius, if this angle is d theta, if you take this distance ds is r d theta, I can write this thing as f into r d theta, then that r becomes torque. So there, work done can be written as torque into d theta. Just like f into s, it's torque d theta. Similarly, power is dw by dt. This will be torque dot d theta by dt. D theta by dt is omega, torque dot omega bar. Just like f bar dot v bar. You can see the formulas, they kind of, look same. Force becomes torque, V becomes omega. So if you get in terms of torques and thetas and omegas, you can use these formulas to get it. Clear with this? So that is one way to figure it out. Now, next thing. Now, there are certain cases, right, where you won't be able to get the kinetic energies, right, for certain systems. I'll show you. We have a concept called instantaneous axis of rotation, IAR. Quite a useful one. We call this thing IAR. So what is IAR? So IAR is an axis. So when a system is moving, translating, rotating anything, right, we can find IAR is an axis about which body can be assumed to be in pure rotation for an instant. Not forever. For a given instant, you can assume it is rotating purely about it. So basically, you're converting that rotation, rolling motion, all that into a pure rotation. Now, if you know system is purely rotating, then the kinetic energy of the system becomes half I about the hinge. So your IAR behaves like an inch for a moment, omega square. So this concept is pretty useful to find actually velocities and energies. We will see how to locate and how to use, but remember this. You can use IAR to find speeds or velocities and energies. Don't use it to find torque, alpha. So torque about IAR is not preferable because IAR rate can be accelerating. It might be a non-inertial train, but energy and velocity के लिए it is fine. Main problem is non-inertial. If it is inertial, then it is fine. So primarily, just remember that use IAR to find the system ka kinetic energy or the velocities. So let me show you an example. Let's say if you have a disk going with V and omega, there is no slipping. Is there any point on the body which has zero velocity? The bottommost point, isn't it? So when the wheel is rolling, we know the bottommost point has a zero speed. Now, in the beginning of rotation, do you remember this statement? When you stand on any point on the body, you will think every point is rotating with omega. Yes. Now, if you stand at A, you think every body is rotating with omega, but your A is at rest. Doesn't this behave like as if A is a hinge? Does the logic making sense? A will think I'm a hinge for a moment. Next moment, someone else will come, but the bottommost point is always at rest. It feels as if the body is purely rotating about this point A. So here, if you see point A has zero velocity, that is a whole catch in the problem. So basically, you're at rest for a moment. Therefore, you're on. It feels like you're on the ground, and the whole body is rotating about you, right? So it feels like you're a pure rotation. So observer at A thinks every point on the body is in pure rotation. Basically, the bottommost point behaves like a hinge for a moment. Now this point won't be constant. For example, after some time, the A would have gone here. So basically, whoever comes to the bottommost point is the IAR. So IAR keeps changing. That's what I said. Taking torque is a bad idea because A has acceleration. In this case, it works out torque also, but generally it doesn't work. So this point behaves like a hinge. Now, since it behaves like a hinge, if you want the velocity of any point, let's say if you ask me the velocity of this point P, I will simply take the distance x and I will say velocity is x omega. Isn't it? If you are having a hinge, what is the velocity of any point? R omega. R is the distance from the hinge. So it feels like the P is going in a circle. Is the idea clear, everyone? So IR is a point, which is like momentarily at rest. So when you go and stand there, it feels like the whole body is in pure rotation. So let me show an example how this works. But any doubts on this page? You can't take any other point. Why? If you take any other point, that is moving, but A is at rest momentarily. So example, let's say if you take our disk, if this was your IAR, now if you take the topmost point, this distance is 2r. So this point ka velocity must be 2r omega, which is 2v because it's not slipping. If you take this point B here, this velocity, this will be r root 2. This velocity must be r root 2 omega, which is v root 2. Now, do you remember how we used to calculate them? We used to calculate them like this. If this is going with v and omega, we used to say, due to translation, we have v forward and rotation is r omega. So that is v plus r omega, and v is equal to r omega, so 2v. This point has velocity v this way and rotation is r omega, which is also v. So it used to go this way with v root 2. Can you see the answers are matching? So when we used to find velocities, this is how we used to find. We used to take translation plus rotation, then we used to add I cap, J cap and solve. But if you go and stand on IAR, ये सब करने का जरूरत नहीं है. Just take the distance from the IAR and finish off R omega. You're done. You'll get the answers. Is this making sense, everyone? Vihan, Soham, Puruja, clear with this? Devika, Ansh, Arnav, Adi, Aryaman, clear? Ahana, Jainil, Vignajit, clear? Vignajit, clear? Okay. So let's see a question on this. In same way, suppose if you want kinetic energy, if you take about IAR, see what will I get? Half IAR into omega square, but half IAR is nothing but ICOM plus MR square omega square. This would be half MR square omega square plus half I center of mass omega square. This is nothing but half VCOM square plus half ICM omega square. This is actually kinetic energy of the system. There. So finding kinetic energy about IAR will give you the kinetic energy of the whole system. You can treat it like a pure rotation. So IAR is pretty cool. Like in this case, right, this is an easy example, so it might feel that way. But I'll show you an examples where it doesn't look that easy and you can't use your regular methods. But got the idea, right? Not necessary, Purvacha. I took an example which you already know. I'll show you cases where even if it is slipping, IR comes. I'll show you a case. I took an example which you can easily understand. I'll show you an examples where it is not like this. Now, first, I want to make sure you are convinced or like, IR karke kuch hai. Then we can go to little more complex ones. So we got a disk. Which is going with V and omega, and it is no slipping. There's a point A here at 30 degrees. Find the speed of point A. How many points on the disk have speed V? V is actually the velocity of center of mass is V. So find the speed of A and how many points on the disk will have speed V. Like I said, if you want to find that speed v, normally what we used to do, we used to find that v and r omega components and stuff. Right, Vihan. Now, if you just want speed, it'll get much faster. You just need to find the distance from this length you have to find, boss. But I'm more interested in the second question. Those kind of questions, na, normal method of doing will be a struggle. So if you find this distance, if you drop a perpendicular, this will be 60. This will be 60. This is r sine 60 and this is r sine 60. If I take this point as O, so OA will be right, Vihan. That will be 2r sine 60 is r root 3. Therefore, velocity of A will be r root 3 omega or v root 3. That's it. That was much easy. Normally you could have taken components and then could have got the magnitude, but yeah. Makes sense? So that is the whole idea, right? IAR will think everyone is going in a circle about it. So it thinks this is going in a circle like this. Is that convincing everyone? Daksha, Puruja, clear? What about the second part? How many points on the disk have speed v? Now ask yourself, from IAR, if you take the center of radius r, so all the points on this circle which are at a distance of r will have a speed r omega, isn't it? There are infinite points. All points on the disk. Just give me a minute. So all points on the disk at a distance of r from IAR. So we have infinite points. That would be a good question. Easy to solve if you know IAR. Make sense? Great. So that means if somehow I can find IAR, I can find the energy there. So how do we find this IAR? So in this case, it was easy to find because the bottommost point was at rest, but every time you won't be so lucky. There are three cases. Now look at the idea, okay? What did I say about IAR? If you go and stand on IAR, you think everyone is going in a circle. Agreed? That means about IAR, every particle, suppose if you have some random body, can I say like this? Every point on the body is going in a concentric circles, isn't it? If you go and stand on IAR, then every point is going in a circle and all the circles are concentric. Do you agree with that statement? That means these guys are going with velocity v like this, and this is going with velocity some v dash like this. Now, for the velocity which is tangential, if I drop a normal for two concentric circles, if you draw any two normals, won't they always meet at the center? If you take any two concentric circles, and if you take normals, any two normals on the circles, they will always meet at the center. Is the idea clear? That means if all the points are going in a circle about IAR, they are concentric circles. If I drop the perpendiculars from the velocities, if I draw the normals, they should meet at the IAR. Consider any two points on the body. And draw normals. Draw perpendicular lines to the velocity. Those will be the normals. The point of intersection is the IAR. Because you said about IAR, everyone is going in a circle. So if I take 2 points, these 2 points will go in two concentric circles. For these two circles, if I draw normals, they should meet at the center. That is the IAR. Is that making sense? The point of intersection is IAR. So case 1 is this. So if you have some random body like this, if this guy is going like this VA, if this guy is going like this VB, you drop a normal, you drop a normal. This point is IAR. Now, one of the common thing we have seen multiple times is this guy. So if you have a rod here, sliding on a smooth floor. So this point A is going this way with VA, and we know this point here is going down with VB. Isn't it? So when a rod is sliding, this is how the 2 points will go. Now, using the same concept, so draw a normal perpendicular to VA, draw a normal perpendicular to VB. This point will be IAR. Make sense? That means if you go and stand on that point, it will feel as if the rod is in pure rotation. If I ask you to find the kinetic energy of this rod, you can't find in a regular way. Because the centrum has itself is going in a circular path and the rod is going in a weird way, we can't solve this. The motion of the rod is very complex. Every point is going pretty weirdly. But if you go and stand on IAR, suddenly life becomes very easy. So if you take that as IAR, see what happens. This distance will be L sine theta. This distance will be L cos theta. I can find a lot of things. Omega is pretty easy to find now. VA by L sine theta. One step mein aa jayega omega. Or I could even take in VB also, VB by L cos theta. And if you want kinetic energy of the rod, I can take half moment of inertia about IAR into omega square. This is the way to do this. The other way is integration. That will be like mind-boggling. It's complex. So the whole idea is that I converted this rod going, sliding. I actually don't know how the rod is going also properly. Next moment, rod will be like this now. That motion is pretty complex, isn't it? Every instant IR is changing, getting it? Every instant IR is changing. But at a given instant, I can find the energy and omega. There, Purojan. If you see this question, it is slipping. Did you see? So IR has nothing to do with slipping and no slipping. It has nothing to do with that condition. So the example previous I took was easy for you to see. Now there, it's an even better example. Is this clear, everyone? We'll do a few problems on this in the next class, but we'll finish on the theory part today. That is one case. But sometimes you have a problem. What if both the velocities are parallel? V1 and V2. Now, from that definition, when you draw perpendicular, there's only one perpendicular. Now, there's no intersection here. That means one thing I'm sure, IR is somewhere on this line, right? Now, you tell me what is same for both the particles? Omega. They rotate with the same omega. So V1 by d plus x must be equal to V2 by x. That's how we can find IR if they're parallel. So if they're not parallel, drop the perpendiculars. If they're parallel, then that will be somewhere on that line. Suppose if you have V1 and V2 like this, anti-parallel. So these are the three cases you have. Now IR will be somewhere in the middle. Now, even if you have taken it outside, the signs will take care of it. This will be V1 by x and V2 by d minus x. So calculate, you'll get x from here. There, these are the three cases you can get. They're not parallel, parallel, anti-parallel. This is how you can look at IR. Clear, everyone? Now you guys try this homework problem. Next class we'll discuss. IR is quite important. We can use to find omegas. We can use to find kinetic energy. We're going to use that again in a chapter called electromagnetic induction in 12th standard. So there again, it will be a savior. We have an incline like this. We have a rod like this. Mass and length L. This angle is 120 degrees. This angle is 30 degrees. This is point A, which is going with speed u. Find kinetic energy of the rod at this instant. Now, if without IR, if you want to do, try and see. But with IR, you'll get the answer. So you have to find the IR of this rod and omega and then do half IR omega square. So try this question. So on Thursday, when we catch up first thing in the class, we will do this. Then we will do maybe one or two more problems on IR. It's not a big concept. Idea is this much only. You could look at IR and you're done. Maybe we'll do one or two more problems and then we'll go ahead with angular momentum. That would be the most critical part of the whole chapter, angular momentum. It's not tough exactly. The biggest problem I notice now, most people don't know how to calculate that. So we will go step by step. We will first learn how to calculate, then we'll do some simple angular momentum problems, then we'll go for complex ones. That should take another 2 classes. I think mostly we should be able to wrap up by next Tuesday. That was one. And next thing, now I'm little confused like what to do with the next chapter. So currently, for all of you, heat and thermo is done in your classes, or fluid is done, or it is going on. Is heat is going on? And that we have a problem because we have a problem with the chapter what to do. So let's see. That is something I need to figure it out. I think most people are done. Heat is started, I guess. Or we can do a completely offbeat chapter like reoptics. Let's see. That is one thing. So I think for one chapter, you guys will have a trouble if it is not done. But I think after that, again, it will be fine. For some of you, all are done. I know. Some of you are super fast. No problem. Okay, we will see that after next week then. Okay, with that, we'll wrap up for that day. This week, a test is online, there till Friday. So make sure to give it.